Okay? On the first day of the unit, we talked about this stuff. We talked about mechanical energy. Okay? What two types of energy make up mechanical energy? Potential and kinetic. Okay, so mechanical energy is made of both potential, okay, in fact we add them together, okay, plus kinetic energy. Now, in order to change the mechanical energy of anything, I have to do what? Work. Okay? Work is a change or a transfer of mechanical energy. So anytime you change either one of these, or both, at the same time, you are doing work. Okay? So if I have this like soap thing on the ground, does it have any mechanical energy in this position and condition?
No.
No. It's not moving and it can't fall any farther. What about now?
Yes.
What kind does it have now? It has potential because it could fall. How did it get that?
Because you lifted it.
Because I lifted it, right. Does lifting it mean I did work?
Yes.
Yes, I transferred some energy to the bottle. I changed the mechanical energy of the bottle by changing, what the heck is going on? By changing the potential energy of the bottle, right? And I did that, okay, again, by doing work. Now, how do you do work?
Transferring energy.
Okay, that's its definition, and yes, but how else? Like, how did I physically make that bottle go from the ground to the desk? Okay, so I use the chemical energy from my food, okay, to do what? When I lifted this, I was exerting what? Yes, I was exerting force against the force of gravity. Okay, so I'm lifting this thing, I'm exerting a force through a distance, right? I moved this bottle through a distance by exerting a force on it, okay? So, work is actually two things. Work is both a change in mechanical energy, okay, remember that delta means change, okay? So it's both a change in mechanical energy and force times distance. Okay? Those are both ways to calculate work, and they're both ways that work is done.
So wait, essentially you're saying we're all Jedis because we can use force?
I'm not saying you can use the force. That would be cool. Okay? But, okay, you can exert a force. Okay?
Good enough.
Yeah. It's not as cool, but it's what you can do. Right? So I can exert a force over a distance on something, and that can change its mechanical energy. In the case of that, okay, I didn't make it go any faster. I just put it above the ground where it then had potential energy. Okay? If I picked it up and winged it at somebody, I wouldn't. Okay? But would I still be doing work in that situation?
Yes.
Yes. Okay? I'd still be exerting a force over a distance, the distance over which, you know, it's in contact with my hand, and I'll make it go.
A distance.
No, I'm exerting the force through a distance. What will happen to this? It will go forward faster, right? What's that?
At someone's head.
At someone's head. Okay? But it'll go faster. I'd be changing not its potential, but its kinetic energy. Okay? It doesn't matter which energy I'm changing. I have to do the same thing. I have to exert a force through a distance. Okay? That could change an object's potential energy, it could change its kinetic energy, or it could change both. Okay? If I throw that bottle up into the air at an angle, not only is it going to go faster, but it's going to go
farther.
Well, or higher, yeah. Okay? And if it goes higher, does it have more potential energy?
Yes.
Okay. So I can actually change both at the same time, but I change them both in the same way. I exert a force through a distance. Okay? Everybody all right with that idea? Okay. The mousetrap. Okay? How does it work? if I want to set a mousetrap, okay, what do I have to do?
Make sure you have a rat infestation.
Well, and I can just set a trap without having an infestation.
What's
There
the
would be
point?
no point, but I could do it.
You have to pull it back and set it.
Right, and when I'm pulling it back, what am I, like, am I doing work there?
Yes.
I'm exerting a force through a distance, right? Where does the energy go?
Stored.
In the spring.
It's stored in the spring, right? I change the shape of the spring when I rotate, just so you know the parts, so you understand what I'm talking about, okay? The spring, the trigger, the catch, and the killing bar. It does have an appropriate name, that is its job. Okay, so what you do to set the trap is you grab the killing bar and you pull it back so that it goes over here. Okay, by doing that, you exert a force through a distance that changes the shape of the spring. When the spring has its shape changed, it can now store elastic potential energy. Okay, so it's got energy due to its condition. It's compressed. Okay. Then I put the trigger, or sorry, the catch onto the trigger, okay, and now it's ready. Okay, it's ready to do something. It has mechanical energy in the form of elastic potential energy stored in the spring. That energy will be released if something presses the trigger. Okay? When the trigger is pressed, what happens to the energy stored in the spring? Yeah, well, it converts it, releases it, converts it into or from potential to,
Kinetic energy.
right? And can kinetic energy do work?
Yes.
Yes. That work will be changing the shape of the little mouse's neck in a undesirable way for the mouse, but a desirable way for you. Okay? So, yeah, it's going to do work. Now, here's the weird thing. Can potential energy do work?
No.
No, it can't. Okay? Only kinetic energy can actually do work. Okay? Potential energy has to be converted to kinetic before it can do anything. Okay? The mousetrap, if not triggered, has tons of energy, but it's not capable of doing anything until that energy is converted into some form of movement. All right? Everybody all right with that idea? Okay? So it's a simple concept. If I exert force over a distance, I can put energy into a system or an object or whatever. Okay? All right, so definition-wise, okay, work is the transfer of energy from one object or system to another. So that's what would be happening when you load the mousetrap. Okay, you exert a force, change shape of the spring. Okay, energy, by definition, is the ability to do work. So, is it like, if you don't have energy, can you do work? And if you can't do work, you can't change the energy of anything, can you? Is this like a chicken and the egg kind of thing? No, it isn't. Everybody knows what came first.
The chicken.
Okay? No, not the chicken. People always ask, what came first, the chicken or the egg? The answer is eggs. Okay? Why? Birds evolved from reptiles. Reptiles lay eggs, therefore eggs came before chickens. So that is no longer a philosophical question. We have settled the debate. Eggs came before chickens. Just so you know. I don't know why people debate that. It seems silly to me. Okay? It's the same as if a tree falls in the forest, does it make a sound?
Yes.
Yes! It forces air out of the way and makes noise. When no one's there to hear it. I don't care, it's physics. Okay? These dumb questions, they're not philosophical, they're physical. Okay? They have easy answers. Okay, so work's a transfer of energy. You have to have energy to do work. This doesn't work like a credit card. Okay? I can't take money that I don't have and use it. I can't take energy that I don't have and use it to do work. I have to have that energy if I'm going to do something. Okay? So when it snowed, okay, and your parents are like, go out and shovel the walk, and you go, I've got no energy. You're lying. Okay? You totally have energy and you totally have the ability to do work. You just don't want to. Okay? Now, if you were laying there and you actually had no energy, you'd be in your bed at absolute zero. Not moving. Then you'd have a legitimate reason to not shovel the drive.
There we go.
You'd also be dead. You know, that's a different thing.
Simple solution.
No, not at all a simple solution. Okay? Just get up and shovel the driveway. Okay?
A small price to pay for salvation.
Yes, exactly. All right, so work energy theorem is a big part of like technology, okay? Especially sports technology, right? And not just the technology itself, but also technique to an extent, right? In something as simple as a tennis serve, okay? If I want to have the maximum speed possible on that tennis ball, okay, there are really only two ways for me to maximize that kinetic energy. Okay? In order for me to transfer kinetic energy to the tennis ball, I have to do work. Right. Okay? And work is force times distance. Okay? The force part is based solely on how strong I am. Okay? If I want to change that part, I got to work out. Okay? I can get stronger, then I can exert more force. Technique and equipment focus on this part of the equation. Okay? I am only so strong. I can only exert so much force. But if I can exert that force over a greater distance, I can do more work. Agreed? Mm-hmm. Okay. So, this is partially why a tennis racket is made of strings and not a paddle. That would be pickleball. Okay? Can you serve pickleball as fast as you can serve a tennis ball? No. No chance. That's why it's a game for older people. Okay? I know there's lots of young people who play it too, but it really is an old person's game. Okay? So, in a tennis racket, having it be made of strings not only means that I can swing it faster because it's got less air resistance, but also means that when I make contact with the tennis ball, okay, so if this is the frame of the racket, okay, the strings actually go behind the racket a little bit when I make contact with the ball. Agreed? Mm-hmm. Okay, the ball kind of sits in here. Does that increase the distance over which I can push on the tennis ball?
Yes.
It absolutely does. If this is a paddle, the ball hits the paddle and bounces off of it, and I get far less distance over which to exert my force, so I cannot serve the ball as fast. Okay? In this case, I can maximize the distance over which I can exert the force. Now, also, if I have good technique, that can also help me to maximize that distance. Okay? If I'm just kind of swinging and I half miss the thing, and it hits like part of the frame, then I don't get a good serve, because I don't get that maximum distance. But if my technique is really good, it stays in the racket for a greater distance, and I get a really fast serve out of it. Right? Does that sort of make sense? Okay? The same is true in hockey. Okay? Back when I was a kid, a hockey stick was a chunk of tree. Okay? It was all wood. They were heavy, they weren't super flexible, okay? And you couldn't shoot nearly as fast as players can today. Okay? Because sticks today can do what? They can flex. And they can flex a lot. Okay? If you've ever seen what some of those sticks do, they're almost 90 degrees when they're leaning on them for a one-timer. Okay? And they're maximizing, again, the distance over which the player can exert their force. Okay? An old wooden stick could flex a little bit. You'd maybe be able to exert your force over that distance. Composite stick? Okay? It's why some people can unload those 90-some mile an hour slap shots. Okay? They've got a greater distance over which it's even more important really for wrist shots. Okay? You can really lean on that stick and bend it. Okay? And in addition to that, if you bend the stick, do you put a little elastic potential energy in it?
Yeah.
Right? It wants to snap back to its original shape. Okay? So you get added speed on that. Okay? It's true in any sport except baseball. Okay? All other sports have embraced some kind of technology, be it for safety, okay, so like football equipment, okay, things like that. Like a helmet, for example. Okay? When you wear a helmet, what does it prevent? It prevents concussions, because an impact to the helmet spreads the energy over a greater area or distance instead of focusing on one part of the skull. Okay? That's where you could get a skull fracture. But if you're wearing a helmet and you're spreading that over a greater area, then less work is done, okay? Because there's also padding in there, okay? That again increases the distance over which the force is exerted, and not as much work is done on your head, which is good. Okay? Golf, same idea, okay? Clubs, the shafts of the club are much more flexible now than they used to be. The ball is even softer, so when it hits the face of the club, okay, so if this is the face of the club here, the ball will actually flatten against the face of the club, stay on the club for a little while longer, allowing you to hit it faster, okay? Exerting the force over a greater distance, okay? All sports, except baseball, have embraced this technology, okay? Or have embraced this idea in some way. Baseball is still a hunk of horse thrown at a stick, okay? Baseball has kind of embraced science, but it's the different kind of science, okay? It's not the physics science, it's more the performance enhancing drugs, okay? Or, actually, also not true, corking a bat. Okay, you guys know who Barry Bonds was? Okay, a famous cheater in baseball. He was corking his bats. So he was taking his bats, drilling them out so that they were hollow inside, filling them with cork, and putting the cap back on, okay? And then he could do what with the bat?
Swing harder?
He could swing it faster, okay? Because it's lighter, right? So he could swing the bat faster, which means he could, crank out home runs because he was hitting a light or using a lighter bat. How'd he get caught?
Didn't his bat break?
Yeah, ruined the structural integrity of the bat. You drill out that bat, okay, sure, it's lighter, but it's also not as strong, okay? So he goes up and hits a dinger, and the bat breaks, and the umpire goes out and goes, this is supposed to be solid, right? But it's full of cork, okay? They took all his home run records away because they had no idea how long he'd been cheating for, right? So all of these things have some sort of physical basis in work energy theory. Okay? Everybody kind of follow there? There's tons and tons of applications of this.
Badminton.
Badminton's still a racket sport, right? Does that go too? All right, now, a bow and arrow, slingshot, okay, anything like that are kind of a classic work energy theorem kind of situation. Okay? When I draw back a bow, am I doing work? Yeah, because I'm exerting a force over a distance. Okay? And when I do that, what I'm essentially doing is pulling the ends of the bow together. Okay? Or I'm putting elastic potential energy in the elastic part of a slingshot or a catapult or whatever. It's all elastic potential energy. Okay? So I exert this force through a distance. I store elastic potential energy in the arrow. So does that mean then that the work I do could equal the final kinetic energy of the arrow? Yeah. If it was a perfect physical world and all the energy was transferred to the arrow, yes. By the way, we only operate in a perfect physical world in this class. Everything works at 100% efficiency, which does not happen in the real world. Okay? So if I do 200 joules worth of work on the bow, then the arrow is going to have 200 joules of kinetic energy when it leaves the bow. Okay? Now, something we'll eventually get to is the formulas for kinetic and potential energy. Okay? Kinetic energy is 1/2 times the mass of the object times the speed squared. So if I knew how much kinetic energy the arrow had, would I be able to calculate how fast the arrow was moving? Okay? Okay? That's where we're headed. Okay? We're headed to using the work we do to calculate some property of an object later. Its final height, its final speed, or something like that. Okay? What it really comes down to is this. Okay? Those two things are equal. The final kinetic energy of the arrow is what it is because of the work I did on the bow. As long as I know all but one of those, I can just do algebra and solve for what I'm missing. Okay? Agreed? Okay. Okay, so work is related to the force exerted on an object. Okay, we know that work is force times distance. So if I exert more force, will I do more work? Yes. Okay? If I, push something with 200 newtons worth of force and then I push it with 400 newtons of force, I'm going to do twice as much work. Okay? It's a linear relationship. Okay? It's also linear for distance. Okay? If I pull back a bow and arrow system, if I pull it back 20 centimeters, then I pull it back 40, okay? Have I done twice as much work? Yes, I have. Okay? All right. Everybody okay with those ideas? Okay. Does mass have an effect?
Yes.
Not on the energy. That's controlled by the work you do. But it can affect properties of the object later. Okay? If I, let's say, apply a certain amount of force to like this very light brush, okay, can I change its velocity by a lot without having to do very much? Okay, if I do exactly the same thing to a bus, I do the same amount of work, but the effect of that work is quite a bit different. The final speed of the bus is not going to be what the final speed of the brush is. Okay? They have very different masses, even though I would have done the same amount of work.
Well, wouldn't you be doing more work because you moved the brush that would contribute to distance?
The brush moved more, but I would say I'm exerting the force over the same distance. So I would start here, I would only push the brush this far. Okay? I would only push the bus that far. So my force and my distance are the same for both, but the effect is different, right? Does that make sense? F and D are the same number, whether this is done to the brush or a bus. The effect that I see is quite a bit different. Yeah, this ends up moving a lot further than the bus is going to go, right? Because the bus has a greater mass. The effect of my work seems less because of the greater mass. Okay? Okay, so here's that situation. Okay, let's say we got this guy here with the golf club. Okay, let's say that he swings as hard as he can. Okay, that means he exerts this much force at the golf ball. Okay, so the golf ball has a very small mass. So his force will produce a very large acceleration. Okay, if he then decides he needs a challenge and winds up and smokes that truck, okay, he's going to do the same amount of work, but he's going to produce a much smaller what? Acceleration, okay? Because the mass of the truck is so much greater. Now, is the truck going to move? If it was on a frictionless surface, would it move?
Yes.
Yes, it would. Okay, not very much. Not like the ball. Okay, the ball would definitely go. Okay, but the truck would hardly move at all. Okay, in the real world, the truck doesn't move. Does that mean he doesn't do any work? Nope, it doesn't. He still does work. Here's how we know. If I'm standing at the front of the truck with my hand on the hood when he hits it, do I know when he hits it?
Yes.
Because I can feel the vibration. That means he moves every particle in the truck. They just don't go in unison. That means the truck slides forward. Okay? But every particle in the truck is going to move, especially where he hit it. Okay? He'll probably put a dent in it wherever he hits it. That still counts as work. He changed the shape of the truck. That part of the truck moved. Okay? Every particle in the truck vibrated. That passed through the truck. Okay? I'd be able to feel that at the other end. That still counts. Okay? Now we're going to follow the relationship between, right? I do the same amount of work in both situations, but the evidence of that work looks different because of the different masses.
So the golf ball particles would all move together?
Yes. Yeah, they would all be in unison. They'd be moving in exactly the same direction together. Yeah. Okay. Okay, so this is kind of what we just talked about here. Motion doesn't mean the movement of an object from one place to another every time. Okay? Most of the time it does. But the vibration through the truck, the change in shape in something still counts as work. Okay? If you stretch a spring or compress a spring, you're not moving the spring from point A to point B. You're just making it longer or shorter. Okay? So you haven't moved the spring, but you've changed something about its shape. And that change in shape can store
Energy.
potential energy, right? Okay, so that still counts as work. Remember, work is any change in mechanical energy, kinetic or potential. Okay? All right. Okay, so we talked about this the first day, but just a quick review here. Work and heat are both transfers of energy. Work transfers what kind? Mechanical. Heat transfers thermal. So they work similarly in that they're both a transfer of energy, okay? But heat is a transfer of thermal energy, which is the random motion of particles, okay? Versus mechanical energy, which is usually the unison movement of an object, okay? All right. I'm going to give you about a 3 or 4 minute break here, and then we're going to talk about potential energy. Okay? So we got to talk about potential energy here. There are lots of different kinds of potential energy. We're going to be most concerned with gravitational potential energy. Okay? We talk a bit sometimes about elastic potential energy. We're talking about bow and arrow, things like that, but we don't actually do any math with it until physics 20. Okay? So we're going to focus mostly on gravitational potential energy, which is energy something has because it is where?
Position.
Yeah, where? Where is its position?
Above the ground.
Above the ground, right. In any position where it could fall. Right? So in order to have gravitational potential energy, something has to be above ground level. What else might affect it? What else might affect the gravitational potential energy of an object?
It's mass.
Its mass. I mean, think about this, guys. You're standing on the sidewalk downtown Calgary and 2 things are falling towards you. One of them is going to hit you. One's a piano, the other's a tennis ball. Okay, I'm pretty sure I'm moving over to the tennis ball. Okay, I'm going to make that choice and take the hit from the tennis ball rather than the piano. Okay, because the piano has way more mass and as a result has way more energy and thus ability to do work on me were it to fall on me. The tennis ball, not so much. Okay, so yeah, mass is definitely, okay, one part of that. The more mass something has, the more energy it can have. Okay, what about height? Definitely. Okay, the higher something is, okay, the more potential energy it's going to have. And something we don't think about because it never changes. Yeah, acceleration due to gravity. Okay. Falling 3 meters on Earth is a long way. Falling 3 meters on Mars is like falling 1 meter on Earth, because the acceleration due to gravity on Mars is 1/3 of what it is here. Okay? If I fall on the moon, okay, if falling on the moon from 6 meters is the same as falling 1 meter on Earth. Okay? It has way less gravitational acceleration, so things don't have as much potential energy at the same height of the moon as they do on Earth.
Does the mass have effect on the speed that it falls?
No. In the perfect physical world, no. Mass, not as much as shape in the real world. Yeah, you're thinking bowling ball and a feather, right?
Yeah, it's
Yeah.
something like
Okay. If you remove the air, a bowling ball and a feather fall at the same rate. Strange. True. Okay. They actually did this on the moon. They had a feather from a falcon and a hammer. Okay. And in the no atmosphere environment of the moon, they dropped them in. It's so weird. I mean, they fell at 1/6 because they're on the moon, so it's like watching it in slow motion. But the feather didn't do this. Okay? The only reason a feather does that is because a feather evolved to be air resistant and allow birds to fly. Okay? So it's designed to catch air and be lightweight and do this. But if you remove the air, everything falls at 9.81 meters per second squared. Okay? Regardless. I think I have a video of that somewhere. Hang on. So, the things that can affect the gravitational potential energy of an object are the mass of the object, the height of the object, and the acceleration due to gravity, which is why the formula for gravitational potential energy looks like this. Mass times acceleration due to gravity times height. Each one of those 3 things has an equal effect on the potential energy of the object. Okay? If I was to double the mass, I'd have how much more potential energy? Double. Okay, if I doubled the height, I'd have double the potential energy. Okay, all of those things have a linear relationship. Whatever I do to one of them, that's what happens to the potential energy. Okay, everybody all right with that? Okay, it's why you're far more afraid to fall 3 meters than 1 meter. Okay, you have 3 times as much potential energy at a height of 3 meters than you have at 1 meter. Okay, it's all linear. Okay, so using this formula is pretty straightforward. Okay, just m times g times h. Okay, manipulating is pretty easy. But here's a question for you. In this situation here, both of these blocks have the same mass. Okay, they're basically identical in every way. This person pushes the block up the ramp at a constant velocity until it gets to the top. This person just lifts it from the ground to the top. Who does more work?
The person pushing it up the slope because they've got more distance to travel.
They have more distance to travel, but they also have to exert less force. They do the same amount of work. This is why the inclined plane is the simplest machine. It doesn't make less work, it makes the work easier. I can do something that I couldn't do directly, like lift that big heavy block all the way to the top of the ramp, but I can get it to the top of the ramp because the ramp supports some of its weight. So I exert less force over a greater distance. It's how the Egyptians built the pyramids. They didn't have help from the aliens. Okay? They used big, long ramps to get these stones to the top of the pyramid. Okay? All right, so yes, they do the same amount of work because this person exerts a big force over a small distance. This person exerts a small force over a bigger distance, but in the end, they do the same amount of work because will both blocks have the same potential energy when they get to the top? Okay, if work's a change in energy, then when they get there and they have the same amount of energy, I've done the same amount of work. Okay, work's a change in energy. Regardless of how the block gets there, its energy changes by X number of joules. Okay, regardless of whether it's lifted or pushed up the ramp. Okay, that is something you must understand, or you will become an inclined plane wrapped around an axis. You will be screwed. Because that's what an inclined plane wrapped around an axis is. It's why screws are good for construction. Okay? You just use the inclined plane to put them in, then you get the added grip of having those little lips that face out versus a nail that you have to pound mercilessly into the wood. Okay. All right. In this situation here, if I lift this 5 kilogram ball, okay, up to this height of 2 meters, and I keep the string tense, okay, when this 5 kilogram block falls, what's it going to do to the 3 kilogram mass? It's going to pull it. Does that mean it'll do work? Yes. It'll increase the kinetic energy of this block. So if at this height, okay, it's got this much energy, okay, when it drops, does the ball keep all of that energy? No, some of it goes to the block. Agreed? Does the energy of the system of the ball and the block stay at 49.05 joules? It does. Okay? The energy can move from one place to another within the system. Okay? And it does. But the total energy of the system will remain the same. If this ball wasn't attached to the block, it would just fall. And it would still have 49.05 joules worth of energy. It would just all be kinetic when it hits the ground. Okay? In this case, because it's attached, it won't go as fast when it hits the ground. So it won't have as much kinetic energy because some of its energy got transferred to the block, but the total amount of energy in the whole system is still the same. Okay, that's that, back to that law of conservation of energy thing here we were talking about. Okay, the energy of a system remains constant, even though the energy might move from one place to another within the system. Okay. So M times G times H, okay? So EP is the gravitational potential energy object in joules, okay? What are the actual units for a joule? Let's figure it out. What's the units for mass? Kilograms. Okay, what are the units for acceleration? Meters per second squared. And what are the units for height? Meters. Okay, if I multiply all of this through, okay, what's meters times meters?
Meters squared.
Meters squared. What's kilograms times meters? Okay, if I got kilograms times meters, I've got kilogram meters squared. They can't change each other. They just have to go together. The meters times meters can make meters squared. The kilograms can't change anything, so they just go together. Okay? Divided by second squared. Okay? Those are the fundamental units for a joule. Aren't you glad we just call it a joule? Okay? But you do need to understand where those units come from. A joule is a kilogram meters squared per second squared. All right, so EP is the potential energy in joules. M is the mass in kilograms. In physics, we deal with mass in kilograms because we deal with things as small as electrons and as big as black holes. Okay, so kilograms are an appropriate unit for mass for physics. In chemistry, we only deal with the small stuff. Okay, so it's grams in chemistry, right? But in physics, it's kilograms. All right, G is acceleration due to gravity, and unless you're told otherwise, that number is 9.81 meters per second squared. And H is the height, always in meters. If they're not in those units, then I don't get kilogram meters squared per second squared. So, okay, got to make sure my units are right. Okay, questions on the formula? All right, so if I wanted to just very simply use this formula to calculate potential energy, okay, in this situation here. So I've got a 3 kilogram box. So there's my mass. Okay, it's lifted by an upward force 1.5 meters above the surface of the earth. That would be my height. They tell me it's Earth, so I know that G is 9.81. All right, so all I have to do is then plug my numbers into that formula. 3 kilograms times 9.81 meters per second squared times 1.5 meters, and I would find that that object or box has 44.1 joules of potential energy. Okay. If I need to manipulate that formula for anything other than EP, what do I do with everything else? Divide it over to the other side. Okay, I mean, that's the beauty of this formula, is that everything is multiplied together. So if I need to find H, I divide M and G over to the other side. If I need to find M, I divide G and H over to the other side. Okay, pretty easy algebra. All right, so let's say we want to find the height of a diving platform that this person is standing on. Okay, so in this question, they give me the mass of the diver. Okay, they tell me that their gravitational potential energy, sorry, that didn't superscript, that should be 5,400 joules. Okay, I want to find H. Okay, so as we said, manipulating this formula is pretty straightforward. I want H by itself. What do I do with M and G? Divide it over to the other side. Okay, so plug in my numbers here. 5,400 joules divided by 55 kilograms times 9.81 meters per second squared. Okay, I'm going to be left with, that person is on the 10-meter diving platform. Okay. Everybody all right with that?
What's the gravitational potential 5.4 if like force of gravity is 9.81?
I used gravity here. This is my energy. The 5,400 is my energy, my gravitational potential energy. The 9.81 is my acceleration. Yeah. Okay, let's talk kinetic energy here. Kinetic energy is energy that does work. Okay? It's the energy of something that is moving. So it's the energy we have to be kind of most concerned with. Okay? Sure, if something is precariously perched on top of a building and has the potential to fall, yeah, we got to be worried about that. But we only have to be worried about it if it falls. Okay? Because then its potential energy turns into kinetic and then it becomes dangerous. Okay? So kinetic energy is the thing that makes things happen. Okay? Kinetic energy is dependent on different things. Okay? Because we're dealing with things that are now moving, okay, we still are concerned with how big they are. Okay? We talked about the piano and the tennis ball. Okay? Does mass still matter for kinetic energy? Mass matters for all kinds of energy. Okay? I mean, a city bus moving towards me at 30 kilometers per hour versus a person on a bicycle moving towards me at 30 kilometers per hour. Okay? The person on the bicycle has way less energy, even though they're going the same speed. Okay? So mass certainly matters. Okay? But what matters more is this. V. Okay? V stands for? Only stands for velocity that has an arrow over the top of it. Speed. Energy is scalar, so we use speed here. Okay? But the speed is squared. Right? So what does that mean if speed increases in terms of what the effect will be on the kinetic energy?
There will be a lot more kinetic energy.
Right. Even small changes in speed result in huge changes in the kinetic energy. Okay? If I went from, let's say, in this situation, if V was 1, 1 squared is 1. Okay? But if I doubled the speed to 2, 2 squared is 4. So I doubled my speed. But what happened to my kinetic energy? I quadrupled it. Would the same thing happen if I went from 1 to 3? How many more? What's 3 squared? 9. I triple my speed, but I've got 9 times now as much energy. Okay? That's what we call an exponential relationship. If I quadrupled my speed, I would have 16 times more kinetic energy. Okay? Speed has an exponential relationship with kinetic energy, and kinetic energy is what does work. This is why there are different speed limits in different places. Okay? How fast can you go through a playground zone? 30 kilometers. Well, you can go faster than that, but not legally, and you shouldn't. Okay? And I'm going to show you why. All right? The speed limit is 30 kilometers per hour. That's about 8.3 meters per second. Okay? If I went through the playground zone at 60, what would happen to the distance it would take me to stop?
And exponentially increases.
It would exponentially increase. It wouldn't double. It would quadruple. Okay, here's why. Work is force times distance, yes? Okay. If I need to stop a car, I need to have my brakes exert a force over a distance in order to make my kinetic energy go from whatever it is to 0. Okay, so let's just say theoretically here that I have a car whose mass is 1,800 kilograms. Okay, and it's moving through a playground zone at the speed limit. 8.3 meters per second. The brakes on the car, we'll just say, can exert 12,000 newtons of braking force. How far will I travel before I stop? Okay. Do my brakes have to do work? How do I calculate work? force times distance. Okay, so here's what we're gonna say. We're gonna say that in this situation, the work done has to change the kinetic energy of the car. We want it to go from whatever it is to zero. Okay. So, work is force times distance. Change in energy is final minus initial. What's my final, I hope? Zero. Okay, so I'm not even gonna bother to put that in there. I'm just gonna put in EK. I want it to change, and whatever, my final is zero, so it really only matters what my initial is. Okay, so can I say this then? That the work is equal to how much I have to change my kinetic energy by?
Yes.
Okay. Do I know all but one of those numbers?
Yes.
Okay, can I solve for D? How? What do I do with F? Divide it over to the other side. Okay, can I plug my numbers in there? Okay. So D is going to equal 1/2 times 1,800 kilograms times 8.3 meters per second, all squared, divided by 12,000 newtons worth of force. Okay. Oh, come on. A watched pot never boils, a watched app never starts. Okay, 0.5 times 1,800 times 8.3 squared. Okay, so that's the top. That's how much kinetic energy I need to get rid of. Okay, what do my brakes turn the kinetic energy into? Heat, sound, okay, all the things that are evidence of energy going into different forms. Okay, going to divide that by 12,000. Okay, so that means that my car is going to still travel 5.16 or 5.17 meters before it stops. And that's going the speed limit. Okay, everybody follow what we did there? You just did your first work energy theorem problem. All work energy theorem problems work just like this. Work is a change in energy. F times D equals the change in the energy. Manipulate and solve. That's all you ever have to do with a work energy theorem problem. Now, the point of this exercise was to show you that exponential relationship with speed and energy. Question?
Why is mass 1/2?
It's more of an average. It's a average change. So that 1/2, it's kind of like that height over 2 thing from here. Okay. So now, let's say we're talking about that car driven by a moron who goes through the playground zone at 60. Okay, so everything's the same except this 8.3, right? Okay, so now, the distance traveled by this car, same brakes, but now it's traveling at 60 kilometers per hour. That's 16.6 meters per second. Okay, divided by 12,000 newtons. Okay, so this ended up being 5.17 meters. I'm pretty sure that's 4 times further, right? 20.7 versus 5.17. Okay, that seems like, I mean, oh, okay, 4 times further to stop. Is that why you should really make sure that you go the speed limit through a playground zone or a school zone?
Yep.
Yeah. Kid runs out in the street. I mean, that's the sign, a kid running out in the street and chasing a ball, okay? If you're going the speed limit, you stop in 5 meters. You're going double the speed limit, thump. okay? Now, I take this kind of seriously because I'm a parent, okay? If you went through a playground zone at double the speed limit and hit my kid, okay, I'm gonna be kind of upset,
Just a little bit.
okay? It's kind of serious, okay? And here's the worst part of it. That change in speed through an average playground zone would only save you about 8 to 10 seconds. You'd probably still be at the same red light as the next person who went through it at 30. Okay, does that sort of make sense? It doesn't really get you ahead to do that, okay? But it can make a pretty big difference, okay? It's 10 seconds to you. It's the difference between having a son or not for me. It's a pretty big deal. Okay? And it can be exacerbated by this terrible habit that I see people have while they're driving. What would that be?
Poor scheduling and planning.
No,
Looking at their phones.
looking at their phone. Okay, I mean, guys, if you're looking at your phone, you don't even react. Then you don't even have a chance to hit the brakes. You only know there's something in the street because
Right.
you hit it. Okay, and I see that happen all the time. Like I'm on parking lot supervision, okay? So I see how many people leave this parking lot like this, okay? It's scary that I have to share the road with those people, okay? And it's scary that I have to fear for my child because your reaction time is so bad, okay? They've actually done studies on this, and they found that distracted driving is worse than impaired driving. Okay? A drunk at the wheel will still react. They're going to react late. That's the problem with impaired driving, is your reactions are slowed. But they'll react. Someone staring at their phone doesn't see anything. They don't react at all till after. Okay? It severely handicaps your ability to react to stimuli around you, which is the most important thing when you're driving. So, lessons to take away. Speed exponentially affects how far you travel before stopping. That's important. I don't know why they don't teach that in driver's ed. Seems like something important, but okay, it's true. It's 100% true. Okay? And paying attention to the surroundings affects your reaction time, which also affects how far you travel. This is assuming you react immediately. If you're looking at your phone, you're going to travel 16.6 additional meters in the second longer it takes you to react at 60 kilometers per hour, because you don't realize you're going 60 kilometers per hour because you're not looking at the speedometer. Okay? It's a big deal. Okay? Take it seriously. When you get your driver's license, it's a big responsibility. Okay? People don't treat it as much as it should be. All right, my rant is over. Okay? But physics, you can't stop it. Okay? This relationship is always there. Exponential. Okay? I double this, I have 4 times more energy. I triple this, I have 9 times more energy. Okay. All right, so as we said, kinetic energy is the energy that an object that is moving possesses. Okay? It is affected by 2 factors: mass and speed. Mass has a linear effect. If I double the mass, I'm going to have twice as much kinetic energy. Okay? But speed has that exponential relationship. Small changes in speed still can affect greatly how far you travel. Okay? When we're in Physics 20, I also showed just how much further you would travel if you were only going 40. Okay? 40 doesn't seem like a big change over 30, does it? Okay? But it almost doubles the distance to stop, even though it's only 25% faster. Okay? It's that exponential relationship with speed and energy. Okay? All right. So any moving object can have kinetic energy, which means it can do work. It's why when we get a Chinook, sometimes people's shingles blow off, or their deck furniture blows off of their deck. Okay? Because the air has mass, and it's moving very fast, sometimes over 100 kilometers an hour. Okay? It can do a lot of work when it hits things. Agree? Okay. All right, so that's what we were just talking about there. Okay, the 1/2 mv squared. EK is the mass, is the energy of the object in joules. M is the mass in kilograms. V is the velocity or speed, actually, of the object in meters per second. Okay, and we still end up getting, when we multiply that through, if we go 1/2 times mass times speed squared, that's kilograms times meters squared per second squared. That's still the units for a joule. Kilogram meters squared per second squared. So they both calculate joules. Okay. Questions on that?
So is it speed or velocity? Because like, would you need to
I-
add direction?
It can be both. Like if they give you a velocity, you can still use it, but you're not ever going to make it negative. Okay? If they give you velocity, you're just going to make it speed. Right? It doesn't matter whether an object's moving forward or backward. It still has X amount of kinetic energy. I have the same amount of kinetic energy at 1 meter per second forward as I have at 1 meter per second backward. Does that make sense? Oh, look, there's the same example. I had it on the slide. I used a lighter car. Okay. Okay. I'd like you guys to write this one down, and we're going to walk through it together really quickly as our first example of work energy theory. So in this one here, we've got a rubber band, and we're putting like a ball in it, and we're going to use it like a slingshot. Okay? When I pull back the rubber band, I exert a force of 60 newtons through a distance of 0.85 meters. What am I doing? I'm doing work. Okay? What kind of energy is now stored in the rubber band? Elastic potential energy, right. When I release that, will the same amount of work now be done on the ball?
Yes.
It'll propel it forward, right? Okay, so can I say this then? Can I say that the work done on the rubber band will equal the change in the kinetic energy of the ball? Yeah, I can. Okay, in the perfect physical world, all of that energy will transfer through. All right, so the things I know here are the force, 60 newtons, the distance, 0.85 meters, which is a really long rubber band, okay? And I know the mass of the ball, 0.125 kilograms. Okay, so if I'm doing work and I know force and distance, I'm gonna expand this part of the formula out to look like this. Force times distance, okay? And then over here, change in kinetic energy means kinetic energy final minus kinetic energy initial. Since the ball initially is just sitting there in a stretched rubber band, what is the initial kinetic energy of the ball? 0. Yeah, it's not moving. It doesn't have any initial kinetic energy. So I can just get rid of that because subtracting 0 is pointless. Okay, do I have a formula that calculates kinetic energy? Can I put that in place of EK final? I can. Right? So force times distance equals 1/2 times mass times the final speed squared. Okay, this question wants to know what is the final speed of the ball. I'm going to isolate that term. How do I get VF squared by itself? What would I do with the 1/2 and the m to move them to the other side? Divide, right? Right now I'm multiplying those three things together, right? The opposite of multiply is divide. So if I want to get VF by itself, okay, that's going to cancel there. What I do to one side, I do to the other. Okay. That solves for VF squared. What do I want? Right, so what do I need to do to both sides? Square root. Okay, now I've isolated VF. Can I plug in my numbers now? I can. All right, so 60 newtons times 0.85 meters divided by 1/2 times 0.125 in your calculator. Top divided by bottom makes a difference. Okay, solves for VF. Ooh, you wouldn't want to get in front of that rock or ball. Okay, it's moving at over 100 kilometers an hour. I mean, you drew back that rubber band like really far. It'd go really fast. It's also not a very heavy ball. Okay, so it would be moving at 28.6 meters per second. Okay, that's pretty standard fare for a work energy theorem question. That's what you're going to be working on tomorrow with Mr. Van Erp. Okay, he's going to have a recording of me going through the solutions to a bunch of examples. So my intent tomorrow is you write down an example, you try it, Mr. Van Erp will play the solution, talk to you about it, move on to the next one. There's going to be a lot of practice of this stuff tomorrow.
Thank you, Mr. Coder.
You're welcome.